Okay, so welcome back again. This is going to be episode 41 of Learning by Doing MPI, and it's going to be part 4 of MPI Environmental Management. And this is going to be possibly the last sort of episode of this series because we have a few pages left and we have, I think, two more code examples to see. So we talked about in the previous episode, we talked about this MPI add error class for your custom error classes that you want to basically generate. And then we were reading, I think, somewhere here. Yeah, we said the value returned by this key is always greater than or equal to MPI error last code. So this is also important. The values should be greater than that because this is the oldest standard defined errors. And then whatever you want to put on top of that is going to have a code which is greater than that. Okay. And it says, again, advise to users the value returned by the key MPI last used code will not change unless the user calls a produce to explicitly add or remove an error class or error code. In a multi-threaded environment, the user must take extra care in assuming this value has not changed. Note that error codes and error classes are not necessarily dense. A user may not assume that each error class below MPI last used code is valid. Okay. And then we have MPI remove error class. Of course, this is also self-explanatory what it does. You got to pass in as an input your error class. This is the value for the error class to be removed. So this one removes a user defined or user created error class. The value of the predefined attribute key MPI last used code associated with MPI COM world is updated to reflect the maximum error class value. Note that there may be unused error classes that have a smaller value than MPI last use code. It is erroneous to call MPI remove error class with a value of error class that was not added by a call to MPI add error class. Once an error class is removed by calling MPI remove error class, it is also erroneous to remove it without first obtaining the value from another call to MPI add error class. It is also erroneous to remove an error class when its associated error codes have not been removed before. Okay. The next thing on the line is MPI add error code. So the previous one was how to add and remove an error class, and the next ones are going to be how to add and remove error codes. So you see that for error codes, you need to associate them with an error class, which could be the one that you have defined. So this could be also a user defined one. You see that. So this is the input, and the output is going to be the error code. So new error code to be associated with error class. Okay. And then you see that these are all integers. So the error class is going to be integer, and this one is going to be an int star. Creates new error code associated with error class and returns its value in error code. To avoid conflicts with existing error codes and classes, the value of the new error code is set by the implementation and not by the user. Next one is basically the cousin of that one, remove error code. You pass in. So it removes a user-created error code and all its associations with any error class. It is erroneous to call MPI remove error code with a value of error code that was not added by a call to MPI add error code. Once an error code is removed by calling MPI remove error code, it is erroneous to remove it without first obtaining the value from another call to MPI add error code. It is erroneous to remove an error code when its associated error string has not been removed before. So you see that for error class, it says that it's erroneous when its associated error code have not been removed, and for the error code itself, it says it's associated error string. So you kind of logically know that what's going to come next. So we started with error class, and then we saw this error codes in the end. We started with error codes next, and now we see that error string here. So we gotta end up with the strings, of course. MPI add error string. So this gets an error code. So it associates a string to this basically error code that you say, error code or error class. That's an integer. You see that integer, and then text corresponding to error code. So that's a CSI string, const char star, and associate a user-defined error string with an error code or class. The string must be no more than MPI max error string characters long, of course. Those stuff, the length of the string is defined in the calling language. The language the length of the string doesn't include the null terminator in C, and in Fortran we don't care about that. Calling MPI add error string for an error code that already has a string will replace the older string with a new string. It is erroneous to call MPI add string for an error code or class with a value which has less than MPI error last code. If MPI error string is called when no string has been basically fed in, it will return an empty string, basically all spaces in Fortran in C. In C is going to be this. MPI remove error string, of course, that is adding a string. The cousin of that or the opposite of that is going to be remove a string, which you're going to pass in the error code, and it's going to remove that string associated to that error code. Removes a user-defined association of an error string with an error code or class. It is erroneous to call MPI remove error string with a value of error code that doesn't have an error string added by a call to MPI add error string. Okay. Calling error handlers. So section 9.3 describes the methods for creating and associating error handlers with communicators, files, windows, and sessions. Error handlers can be invoked implicitly when errors are raised during MPI operations, but can also be called by the user. So we have MPI call error handler. So this one gets a communicator. Whoops, that was too thick. It gets as an input the communicator with the error handler, and then it gets the error code associated to that. So this is MPI call error handler. That simple. It says this function invokes the error handler assigned to the communicator with the error code supplied. This function returns MPI success in C and the same value in I error if the error handler was successfully called, assuming the process is not aborted and the error handler returns. So I put an X again here, so you see that call error handler also exists for Windows, for files, and for sessions, but we put an X there. We don't care about them. Okay, now we can jump back safely to this example we had. You see that final call also is running in the background. So this is it. The first portion, we're not going to talk about that. We have error class, error code, and then we have the string, error string, and then the result length. We create a new error class by a call to this function MPI add error class. We pass in our error class there. We associate an error code to that error class, and that is MPI add error code. We do this. And then adding an error string, we associate a string to that error code. So we say your house is on fire. Quite ironic. And then MPI error string, we use that to basically get that string into that string. Kind of dubious in this here. And then we have the root process only printing MPI error last code. That's the MPI error last code. Kind of, a little bit messy maybe. And then after that, we immediately basically say custom error code, and then we pass in sort of that string which we got here. And then check the MPI last used code as well. So we remember that one was sort of an attribute associated to that communicator MPI world. So that is why we retrieve it with MPI get attribute, and then we pass in sort of the key of MPI last used code, and then this is the value associated to that. And then the root process is going to basically print that value for you. And then again, doing something I forgot to pass in this freeing comment here that I usually do. So you got to remove the error string, you got to remove the error code, and then you got to remove the error class. So very simple example. So MPI user defined error classes. Oops. So there we go. This is the last code, the MPI error last code. This is a huge number. And we have the custom error code. This is the code which is associated to that. And you see that this is the last code, which is 107.374.1823. And you see that these digits are sort of the same up until here with this one, 37.4, up until this point. And then you see that this one starts with 1, but this one starts with 2. And that is why we said always the custom or user defined ones should have or must have an error code which is higher than this value which is provided by the standard ones. And then this is the string associated with that, which says ironically that your house is on fire. And this is the MPI last used code, which has this value, which I don't know why this value is not greater than what we see with. So the error code we see is this one, but the MPI last used code is actually not reflecting whatever you are adding on top. I don't know what is MPICH doing behind the scenes, but this should have a reasonable explanation. But this value is not even comparable to the code that we have here. Because in terms of sort of digits, you see 2, 4, 6, 8, and 10. So this is a number with 10 in digits. And this one is 2, 4, 6, 8, and 9. So this is clearly smaller than this MPI error last code. I don't have any explanation for that, and I have no idea why that is the case. But I just wanted to show you that you can get that MPI last use code with this MPI get attribute. Okay, so the final thing for this chapter is timers and synchronization. MPI defines a timer. A timer is specified even though it is not message passing, because timing parallel programs is important performance debugging, and because existing timers in POSIX, they're problematic or they are inconvenient. Or they don't have adequate access to sort of high resolution timers. So MPIW time is the first one. MPIW time returns a floating point number of seconds representing elapsed wall clock time since some time is in the past. The time in the past is guaranteed not to change during the life of the process. The user is responsible for converting large numbers of seconds to the units that they prefer. This function is portable. It returns seconds, not ticks, and it allows high resolution as well. So this is a very simple example. I don't know why I didn't put, okay, I forgot to put also the examples there. I'm going to correct that one maybe later, but for this one, I do have an example. Let's see. I think it was MPI timers. Yes. So this is MPI timers.c. I forgot to add that one there. I'm sorry for that. I'm going to put it up here. So I'm going to save this. Okay. And this is a very simple example. We do have a very simple structure similar to what you see basically here. So you have the W tick before doing something specific, and then you say this is the timer resolution. This is actually the W tick basically gives you the resolution, and then the next thing on the line is the times returned are local to the node that called them. There is no requirement that different nodes return the same time, but see also the discussion of MPIW times global before. We already talked about that. And then this is MPIW tick. I'm sorry, I think I mispronounced this one. The first one we had was MPIW time, and the next one is MPIW tick. I'm so sorry. I think I mispronounced. So let me add this one before I do more mistakes. MPI timers.c. Was it timers? Yeah. So MPIW tick returns the resolution of MPIW time in seconds. That is, it returns as a double precision value the number of seconds between successive clock ticks. For example, if the clock is implemented by the hardware as a counter that is incremented every millisecond, then the value returned by MPIW tick is going to be 10 to the power minus 3 or 0.001. And this is why I used MPIW tick, but the first thing was MPIW time. Sorry. So the pattern here is that you're going to have a start time. You put the MPIW time before you do something specific, and then you do some stuff in between, and then you put the end time, and then you call this MPIW time again. And then the elapsed time is going to be, of course, end time minus the start time. So we have the same pattern here. First, we try to print with with the help of this MPIW tick, the resolution, the time resolution that we have. And then we're going to have the start time. We're going to call this MPIW time. And then we're going to do something very dubious or stupid. We're going to do, how many zeros I put here? I have no idea. It's 10 million if my eyes can see correctly. Yeah, it is 10 million. So for 10 million, we're going to do some stupid sort of summation, and then we're going to do this sort of end time and see how much time is elapsed in between. And then we're going to print that. Every process is going to print that how many seconds basically it is elapsed. Oops, I shouldn't have done that. Let's save this, MPICH, MPI timers, and let's run that with 8 processes. You see that our timer resolution is 1, 2, 3, 4, 5, 6. So it's 1 microsecond. Impressive. And every process, you see that it gives sort of a different elapsed time. And you already remember that that MPIW time is global was false for my case. And you see that in this case, we are getting different times which are elapsed. They're not, let's say, orders of magnitude different from each other, but you see that, for example, up until this digit, yeah, I think all of them are starting with 0.036, and then the next digit is going to be different. For all these processes starts with 3, and then this one starts with 4, 5, 5, and then 8. Okay, so that's it. I think this was the end of this chapter. Yeah. Then the next one is going to be chapter 10. I think we still have 7 minutes left, but I'm going to stop here because we're not going to proceed to the next chapter. And I do hope that you learned something from this video and all the previous episodes within this chapter. And I hope to see you in the next one.